Hi everyone, today we are going to look at partial fraction decomposition. It's another one of those methods you will encounter quite a lot when doing integrals. So let's start with some simple rational function, something like this, 2x minus 1 over x squared minus x minus 6. So it has an important feature that is common in most of the rational functions encountered so far in integral calculus, which is, if you look carefully, you will notice that if we have a function y equals to x squared minus x minus 6, you'll see that its derivative is 2x minus 1. So here, because the top, if you remember, if the it's just a log of f of x. Of course, you have to plus a c. So if the numerator is the derivative of the denominator, then it simply is the log function. So in this case, obviously, it's log x squared minus x minus 6 plus c. Of course, the numerator doesn't have to be exactly the derivative of the denominator. You can have a linear multiple as well. So for example, if say 4x minus 2 over x squared minus x minus 6, then it's really just 2 times 2x minus 1 over x squared minus x minus 6, and it leads to exactly the same result. Well, not exactly, it's double result, but you get the idea. Yeah. So all of these are very simple to solve. Today we are going to start looking at situations where this is not the case. So for example, this one, 3x plus 11 over x squared minus x minus x. So as you can see here, derivative, well, the denominator is exactly the same. So the derivative of the denominator is 2x minus 1, and there is simply no way you can change this to get to 2x minus 1. So what do we do? Well, if you are very observant, you would realize that, well, by observant, if you have a genius level, you will realize that 3x plus 11 is actually x minus, sorry, let's start from the start. So x minus 3 times x plus 2, and interestingly enough, if you have two numbers, say if you have 4x minus 3 minus 1 over x plus 2, just bear with me for a minute, equals to 4x plus 2, x minus 3, x plus 2, and then plus x minus 3 over x minus 3, x plus 2. So we actually end up with 4x 8. Wait, this is minus what I'm doing. Minus negative 3, so you actually end up with 3x plus 11 over x squared minus x minus 6. So what we can say is that 3x and this expression is the same as this expression. Yeah. Of course, I can do this because I already know that this part is the case. So here, now what we can do is we can simply integrate it as integral of 4 over x minus 3 minus 1 over x plus 2 and dx. And here it's pretty straightforward because we know this is 4 and the derivative of x minus 3 is 1, so it's 4 log x minus 3 minus log x plus 2 and then plus c. So we know if we can do this, then it's much simpler to integrate these rational functions. So can we do this even if we don't already know that this portion is true beforehand? The answer is, in fact, yes. Otherwise, this topic wouldn't exist. So this is the theorem of partial fraction. So if we have a function that can be expressed as a rational function, where you have a polynomial over the product of two polynomials, given that the degree, so the polynomial in the numerator has less degree than the product of two polynomials, then you can always break it down into something over the first factor of the denominator plus something over the factor of the second denominator, as long as the degree of the numerator is always lower than the degree of the denominators. In fact, this decomposition always exists, and it's always unique. Of course, the proof, it's pretty long, so I'm not going to go through it here, but if interested, I'm including the link in the description. So now we know that's the case, so we are going to actually have a look at how to perform this decomposition. In this example, the denominator has already been factorized for you, and the main focus is just to perform the decomposition. We're just going to, because we have two factors here, so we have our first x minus 1 and x plus 3. So we are going to separate them into x minus 1 plus x plus 3, and with something so a term that's one less degree than the denominator in the numerator position, and we don't know what they are, so we're just going to call them a and b. Okay, once we have that, we can work out what a and b are respectively by firstly multiply everything by the denominator. So let's use a red pen, actually make it smaller. So multiply everything by x minus 1 and x plus 3 times x minus 1 and wait, what am I doing? X minus 1 and x plus 3. So what this does is that it can eliminate everything. So eliminate a denominator here and make everything easy to work with. So we end up with x plus 1 equals to a. X minus 1 cancels out with x minus 1 with x plus 3, and then plus b. X plus 3 cancels out with x plus 3, so we end up with b x minus 1. And now we can try to solve this all. So let's say x plus 1 equals to, we're going to expand them first. So ax plus 3a plus bx minus b. So we gather the like terms, a plus bx plus 3a minus b. So we gather all the like terms together, x terms, constant terms, and now we can match the coefficients. So as you can see here, coefficient of x is 1, and the coefficient of x here is a plus b. So a plus b has to be 1, because there is no other coefficient of x exist anywhere else in this equation. And similarly, 1 matches us with 3a minus b. Once again, there are no other constant terms other than 1 and 3a minus b here, so they have to be equal. And what this gives us is a pair of simultaneous equations. So what we have is a plus b equals to 1. We can add them. Plus 3a minus b equals to 1. That eliminates the b for us, so we end up with 4a equals to 2, which means a equals to a half. And because a plus b equals to 1, b has to be a half as well. And then substitute everything back into the original expression, and we end up with half over x minus 1 plus half over x plus 3 dx. And of course, we can move the constant term a half outside, and x minus 1 plus 1 over x plus 3. As you can see here, this is much easier to integrate because this is simply 1 is derivative of x, so this is log x minus 1, this is log x plus 3, and then plus c would gives us the integral. Okay, so the method overall is pretty straightforward, and we'll have a look at another potentially slightly faster method in the next example. So we don't even have to worry about integral, we go straight into decomposition. So once again, the factors have already been given to us, so all we need to do is just to separate them. So we end up with x minus 3, of course there's something above it, and then plus b over x plus 1. So once again, we have two unknowns, two constant terms. So because the numerator has to be of a lesser degree than the denominator, so this is degree 1, so this will be degree 0, and we already know that they have to be constant terms. Once again, first step is always to get rid of the denominator here. And of course you do it to both sides. Now we end up with 3x minus 5 equals to a times x minus 3 cancels out with x minus 3. So we have x plus 1 plus x plus 1 cancels out with x plus 1, so it's b times x minus 3. Here it's we can expand everything and match the coefficients, or we can eliminate a to find the b and eliminate b to find a by choosing the appropriate x values. So let's eliminate b first. What will eliminate b? Of course, x equals to 3. X equals to 3, so you end up with 3 times 3 minus 5 equals to 4 times 3 plus... Oh, sorry, this is a. My bad. 3 plus 1, 3 minus 3, 0, b gets eliminated. So we end up with 9 minus 5 is 4 equals to 4a, and of course a equals to 1 here. And then we do exactly the same thing to eliminate a and find the b. So in this case, x has to be negative 1. So 3 times negative 1 minus 5 equals to, a gets eliminated, so we only have to worry about b. So b equals to negative 1, so b is so this is -4. Okay, so 3 times -1, -3, so -8 equals to -4b. In that case, b equals to 2. Let's highlight our numbers so again we don't lose them in the mess here. Alright, so once we get that, we just substitute these numbers back in x minus 3 plus 2 over x plus 1. So 3x minus 5 over x minus 3 times x plus 1 can be decomposed into 1 over x minus 3 plus 2 over x plus 1. Okay. It's pretty straightforward. The takeaway here is once you are at this stage, eliminate by choosing x values that will eliminate b, you can find a, and by choosing x values that can eliminate a, you will find what the b is. It's really pretty straightforward. Things can get slightly more complicated when the numerator may have a higher order than the denominator. So in this case, obviously order 3, order 2, so we can't decompose it directly. But what we can do is we can just factor a term out of factor something. Well, factor a factor of factor a factor out of the numerator. So what we can do instead is we can take something out of the denominator, so what's left is strictly of lesser degree than the denominator. Sorry, factor something out of the numerator. So we end up with we can do this, ax plus b. Let's assume that this is what we managed to factor out from the top, from the numerator. Yeah, let's make it equal. So here, then, because we have factored out a term, so we can know that what's remaining is of lesser degree than the denominator. So it's a over, this is x minus 3 and actually no, it's x minus 2 and x minus 1, so we end up with a over x minus 2. Sorry, this should be a third term. It's not a, it's c. So c over x minus 2 plus d over x minus 1. And here, once again, we multiply everything by the denominator to go forward. Equals to ax plus b times x minus 2, x minus 1. And then plus minus x minus 2 cancels out, so it's c x minus 1, and then plus d x minus 2. Okay, so in this expression, what we can do first is to actually find what a is, because here we have a coefficient of 1, and on the right hand side, a is the only term that's going to have x cubed, because if we expand everything, which we're not going to do because it's going to be very messy, but if we expand this, we have ax times x, which is ax cubed. So this is the only part where there is a cube term, and a will be the, if you expand everything, will also be the only expression that have a cube term attached to it. So we can safely say that x cubed equals to ax cubed, which means a equals to 1. And then we can use the method we used previously to find what c and d are. So to find what c is, we make x equals to 2, so we can eliminate everything else, including this one, because 2 minus 2 is 0, so this disappears. So 2 cubed plus 2 minus 3 equals to, this part is gone, so equals to c, 2 minus 1. Okay, d is gone as well because it's multiplies 0. So 2 is 10, 10 plus 2, sorry, 8 plus 2 is 10, 7 equals to c. Yeah, so c equals to 7. And we can do the same thing to find what d is, making x equals to 1. So 1 cubed plus 1 minus 3 equals to, of course, this disappears because x minus 1 is 0. This also disappears. So we end up with d times 1 minus 2. So minus 1 equals to 2 minus 3 minus 1 and minus d. So, of course, it means d equals to 1. And finally, we want to find what the b is. So the quickest way for me is just to, because we already know what c and d are already, so we can just make a disappear. You don't have to do that, but for me it's more convenient. So let's set x equals to 0. That surely will make a disappear. So once x is 0, so negative 3 equals to b times 0 minus 2 is negative 2, 0 minus 1 is negative 1, then plus what's c? C is 7, minus 1 plus 1, 0 minus 2. So we end up with negative 3 equals to 2b plus, well, actually it's minus now. Negative 7, negative 2, so minus 9. Of course, the implication of that is 2b equals to 6 and b equals to 3. So we have found our all four numbers. Highlight them to make them easier to see. And once you substitute all of them back into this expression, it is x plus 3 plus 7 over x minus 2 plus 1 over x minus 1. So as you can see here, this is way easier to integrate than this expression. You just have some x squared term, some x term, and then two log expressions, and that's it, rather than like not actually sure how to do this. So that's it. So with the moral of the story is, when you have a numerator that's of a higher degree than denominator, you can always factor something out to make sure what's left of the numerator is of a lesser degree, of a lower degree than the denominator. Okay, next one. This is instance an alternate method in breaking a rational function into partial fractions. This is often called the cover-up rule because you pretend the others don't exist or something. I'm not sure, but it's usually it's often a quicker way to decompose partial fractions, especially when there is more than two factors in the denominator. So let's just break everything down. We know that it's gonna be, this part is gonna be exactly the same as all the previous ones. Alright, so look at that. What we can do now is to deal with one factor at a time. So let's only look for a. So we just have to multiply everything by x plus 1. So by multiplying x plus 1, we will end up with 7 minus 5x over x minus 2, x minus 3. We end up with a plus b, x plus 1, x minus 2, plus c, x plus 1, x minus 3. So here, obviously, we set x equals to -1 to eliminate everything. So we end up with 7 minus -5. So it's 12. -1, -3, -4 equals to a. Yeah, equals to a because both of these terms have been eliminated. We end up with so a equals to 12 -3. So a equals to 1. Okay. Next one, we can do the same thing to get b. So we multiply everything by x minus 2. So we end up with 7 minus 5x. Because minus 2 has been eliminated, so we're x plus 1, x minus 3 equals to equals to a x minus 2 over x plus 1 and plus, okay, b is only 1 left, and then plus c, x minus 2 over x minus 3. Alright, so once again, by setting x equals to 2, we eliminate both a and c terms, and all we have is 7 minus 5. So actually, I can do just in my head. So 7 minus 10 equals to -3 over 3 times -1 equals to b, which means b equals to 1 as well. Okay, let's highlight them just in case not to forget. I'm sure you know the process by now. We multiply everything by x minus 3 and then set x equals to 3. So that would end up with 7 minus 5 times 3 over, because x minus 3 get cancelled out, so we only have 3 plus 1 and 3 minus 2. And then other side, because everything's multiplied by x minus 3, then we only have c left. So I'm just skipped a few steps, so I just skipped this by combining them into 1. So in this case, 7 minus, it's -8 over 4. Okay, negative. So actually, this is just plain 4 equals to c. So c equals to -2. I substitute everything in. We end up with. Actually, let me highlight this. And so we end up with 1 over x plus 1 plus 1 over x minus 2 plus -2 over x minus 3. Or alternatively, actually, you know what? Just make it minus. Yeah, so here is your partial fraction. Alright, next one. it's slightly more complicated because you actually have a quadratic term here. The issue with quadratic term is when you decompose it, x squared plus 4, you can't just assume that this is a constant term, because when you decompose according to the theorem we have earlier, the numerator just has to be of lesser degree than the denominator. So when a denominator has a degree of 2, 1 degree is lesser. So we can't just assume it's a constant term, and we actually have to begin with assumption that this is a polynomial with 1 degree less than the denominator. So we use bx plus c instead of just b. Of course, start is exactly the same. We multiply everything by the denominator, so we end up with 3x plus 10 equals to, so multiply this, so a x squared plus 4 plus bx plus c times x minus 2. Okay, so here, to find a, it's pretty straightforward. We just make x equals to 2 because 0 gets rid of this one. Yeah, so x equals to 2, so we have 16 equals to 8 times 8. And then everything else disappears, so a is actually 16 divided by 8, which is 2. Now, next one. Let's find b. Okay, b, it's you can't really eliminate a because there's no real x value that will make the whole thing disappear. So we have to try something else. What we can do instead is to recognize the fact that a times a will be x squared, and b x will times x if we expand this as well. So bx times x will be x squared, and we have ax squared. So what we actually end up with is ax squared, and then plus something, 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 and then plus bx squared plus something, 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 something. Yeah. What they are is not really important because we only look at on the other side. There is no square term, so the coefficient is 0x squared plus something, something, something. And as you can see here, because ax squared and bx squared are the only x squared terms here, and the 0x squared is the only x squared term, so we can safely say that a plus b has to equal to 0. And of course, we already found that a equals to 2, so b has to be negative 2. Okay, and then finally, we want to find what c is. Because we already know what a is, so we just have to eliminate b. So we set x equals to 0. Actually, any number will do, really. But 0 is convenient because 0 just makes bx disappear. So and make a lot of other things disappear as well. So simplify things. So we have 10 equals to a is of course 2 times 4. Plus b disappears, so we have c times negative 2. 0 minus 2 is negative 2, yeah. So 10 equals to 8 minus 2c, and so c equals to negative 1. Okay, so we have found our all 3 terms. And we just substitute everything back in. And we end up with 2 over x minus 2 plus Actually, just make it minus. Really, it's probably easier. Minus 2 over x squared plus 4 minus 1 over x squared plus 4. And so that's pretty much it. Only thing is, if there's no easy way to eliminate that term, you can always matching coefficients to find out what those numbers are. Okay, and last one. Let's look at the one with the repeat factors. One thing about repeated factors is that you have to consider both the factor that on its own and when it's repeated. So we should have a over x minus 2, but you have to also consider the repeated part as well. And then plus c over x plus 1. Once again, you just multiply everything by the denominator, so you have 8 minus x equals to a. Negative 2 cancels out, so x minus 2 plus, sorry, my bad, is a plus 1 there as well. X plus 1 plus b, x plus 1, and then plus c, x minus 2 squared. Yeah. Once again, we can do it, eliminate these terms by one. Yeah. So obviously b and c are the easiest to find first, because by setting x equals to 2, we can eliminate all of both a and c and just have a b. So 8 minus 2 is 6. A is gone, c is gone, so we just b 2 plus 1. So which gives us b equals to 2. Yeah, because 2 plus 1 is 3. Let's highlight this so we do not forget. Next one, by making x equals to -1, we eliminate this and we eliminate b, and we can find what c is. 8 minus -1 is 9, so equals to c times our -1 minus 2 squared, which gives us 3. So 3 squared is 9, so c equals to 1. Okay. Once we have found both b and c, we can just find what a is now. In this case, I'm just going to use, once again, x equals to 0 because it's convenient. So 8 equals to a times 0 minus 2 is minus 2. X plus 1 is 1. 0 plus 1 is 1. And then plus, what's b? b is 2 times 0 plus 1, so it's actually 1. Oh, wait. What am I doing? 1. And then plus c. c is obviously 1 times -2 squared. And so 8 equals to -2a plus 6. So obviously a is -1 here. And then in the end, I can just write everything down as -1 over x minus 2 plus b b is 2 over x minus 2 squared plus c is 1 over x plus 1. And here is your partial fraction decomposition. And so there is that.